In this lesson, we're going to look at what we mean by even and odd symmetry. And so we're going to start out with what we mean by an even function. Now, an even function is a function is where f of negative x is equal to f of x for all x in the domain. Now, in a little bit, we'll look at what this means about the symmetry. But in an even function, it's symmetrical about the y-axis. So if you have a point xy, then there's also going to be a point negative xy, or the opposite xy. Notice there that your x's are opposites, but your y's are the same. And so that's going to be symmetrical about the y-axis. And then for an odd function, if it occurs, if f of negative x is equal to the opposite of f of x. Notice these two, it's going to be the opposite of f of x for all x in the domain. And we will see that an odd function is symmetrical about the origin, or in a case where if the x's are opposites, then your y's are also opposites, is what occurs when it's an odd function. So let's look at a couple of functions and see how we would go about testing this to see if your function is odd or even. And there are some functions that are neither. Not every function's even, not every function's odd. So some are just going to be functions that have no symmetry. And so let's take this first one. If we have f of x is equal to x squared plus 6. Now, our test says that we're to take this function and substitute in f of negative x. So I would put negative x squared plus 6. If I evaluate this, negative x squared is equal to x squared plus 6. So notice I got the exact same function as what I started with. And I've got x squared plus 6, x squared plus 6. So that's what this is saying is if I substitute in negative x into my function, I still end up with the same function. So this would be an example of an even function. Okay, let's look at another one. Let's say we have f of x is equal to 2x to the 4th plus x squared minus 2. Well, if I substitute in f of negative x, then I have 2 times negative x to the 4th plus negative x squared minus 2. Well, the opposite of x to the 4th. If you raise a negative to the 4th power, you get a positive. So I end up with 2x to the 4th. Negative x squared is going to be x squared minus 2. So again, I ended up with the exact same function that I started out with. So this again would be an even function. Now, in a second, you're going to start seeing that the reason these are named even, and there's a way that we can look at our function sometimes and tell. Notice in this one, my exponent was a 2. 2's an even number. Now I had a constant, and if we put a variable with that constant, we would have to put x to the 0, because x to the 0 is equal to 1, and 6 times 1 is 6. So anytime you have a constant term, and we talked about that earlier when we talked about the degree of a constant was 0, because that's what your exponent would have to be. And again, down here, my exponent's 4, 2, and 0. So when you look at this, when it's an even function, then that means all of your exponents were even. And so that's how you can look at a function and know that it's going to be an even function. Another example would be f of x equals x to the 6th plus 2x squared plus 3. Again, this would be an even function because all of your exponents are even. And so that's where the name came from, and that might help you remember as you're dealing with your function, but the test is to substitute in negative x. So those are some examples of even functions. Let's look at some odd functions. Now, it says for an odd function, if you substitute in the opposite of x, then you get the opposite of the function. You get the opposite y. So let's see what that would mean as we start working with it. Let's take a function. F of x equals 7x cubed minus x. Well, if we substitute in a negative x, okay, when you cube a negative, you get a negative. So this is going to end up being negative 7x cubed, and the opposite of a negative is a positive, plus x. So you can see we did not end up with the same equation that we started with. Here we have negative x cubed, up here we had positive x cubed. Here we have positive x, here we had negative x. But notice we ended up with the opposite of each one. And so that's going to tell us then that we have an odd function. Now, another way of doing this would be to take this function and factor out a negative 1. If we factor out a negative 1, then we'll have 7x cubed minus x. So we ended up with the opposite of the equation that we started with. And that's the way that it's written. F of negative x is equal to the opposite of f of x. And so we did end up with the opposite. So this would be an example of an odd function. And so if you look here, your exponents are 3 and 1. Well, those are odd numbers. So that's going to help us as we look at our odd functions to know if they are, that they are. If we had f of x equals x to the 5th minus 2x cubed, plus x. Well, substituting in the opposite of x, we'll have the opposite of x to the 5th minus 2 negative x cubed plus negative x. Well, if you raise a negative number to an odd power, you get a negative. So that's the opposite of x to the 5th. You raise a negative number to an odd power, you get a negative. So we're going to have negative x cubed times negative 2 would make that a positive 2x cubed, and then negative x. Well, again, I had negative x to the 5th. I started out with positive x to the 5th. I have positive 2x cubed, started out with negative 2x cubed. Negative x started out with a positive x. Everything turned out to be the opposite, or if I factor out a negative 1, then I'll have 2x cubed plus x. When I factor out a negative 1, my signs change. So I ended up with the opposite of what I started with. So this would be an odd function. And again, if you notice, each of your exponents was odd. Now let's look at this one. F of x is equal to x cubed plus 1. If we plug in a negative x, okay, a negative cubed is a negative. Now we look at this one. My x's are opposites, positive x cubed, negative x cubed, but my numbers are the same. So this would be neither. It's not the same function, but again, it's not the opposite of that function. If we factored out a negative 1, we would have the opposite of x cubed minus 1, not x cubed plus 1. So this would be neither odd nor even. And if you notice, we've got an x cubed. Here again, for the constant, we would have to put the 0. And we consider the 0, if you consider 0 as odd or even, then you consider it to be even. And so this would be neither. And so for the odd ones, you have to have a variable with every term would be another way of looking at it. We can't have a constant term in an odd function. You have to have a variable to every term, and your exponent has to be odd. For an even, we can have a constant, but all of the terms that have exponents have to have even exponents. And so then you can also have ones that are neither. Let's look at one more. Say that we have f of x is equal to x squared minus 2x minus 5. And we know that this is going to be a parabola, but let's substitute in f of negative x. So negative x squared would be x squared. Then negative 2 times negative x would be a positive 2x minus 5. Well, notice these are the same, but these are opposites. These are the same. So we don't have them. It's not the same, so it's not an even function. They're not all opposites of each other, so it's not an odd function. So this one would be neither. It has no symmetry about the origin or about the y-axis. Again, the final test, or the test that will always work, is factor out a negative 1, and you can see we don't end up with the same function that we started with. It's not the opposite of our function that we began with. And then we talked about the symmetry, that a function that is even is symmetrical about the y-axis. So an example there of what's going to happen, if we just graphed y equals x squared, well, we can see that that's going to be an even function. And so what ends up happening is, if you know what your value is at positive 1, which 1 squared is 1, then you also know that you have that same value at negative 1. Because what it means is, if you've got a point xy, then you will also have the point the opposite of x, but you'll have that same y. And so at 2, we have 4. So the opposite of that, at negative 2, we would have 4. And we would have our parabola. And that's symmetrical about the y-axis. And what it's going to do, it'll help us as we graph our functions. If we know that they're an even function, then we're only going to have to find values on one side, and we can reflect them across the y-axis to those values on the other side. But that would be an even function. Now, an example of an odd function, let's just do y equals x cubed. We'll keep these pretty simple. For y equals x cubed. Now, what that means is, for your value of x, then you're going to get your opposite. Oops, let me put it this way. F of negative x is equal to the opposite of f of x. That means your y, when your x's are opposites, your y's are opposites also. So we know we have 0, 0. Well, 1 cubed is 1. So that means for negative 1, we're going to have negative 1. When I use the opposite x, I got the opposite y. Well, 2 cubed is 8. So for negative 2, we're going to have negative 8. And our graph is going to look something like this. So that's being symmetrical about the origin. For every x, y, you're going to have the opposite of x, the opposite of y. And so you can find your point. So again, if we know that it's symmetrical about the origin, then we only have to find points in one quadrant, and we can then know those points in the opposite quadrant. And so we have then what's called an odd function. and deal with our symmetry that way. So we have odd and even, and we can tell if a function is odd or even by going through a test. And then knowing that a function is odd or even will help us as we begin graphing. The other thing we're going to look at is the greatest integer function. Okay, I really want to look at a graph first, and then we will get into what we call our greatest integer. But there's several situations that you end up with graphs that we might call them step functions. And the graphs are very distinctive when you've got a graph that is a step function. And there's some specific times that you're going to see this. Let's say you went to the post office to mail a letter. Well, if the letter weighs up to 1 ounce or not over 1 ounce, up to and including 1 ounce, you're going to pay 44 cents. Now, it doesn't matter if it weighs a half of an ounce or a fourth of an ounce. Up to 1 ounce, we'll make this one 1, 2, 3, 4, and 5. Up to 1 ounce, you're going to pay 44 cents. So we're not going to start this at 0, and when we don't, we put a little break there. But let's say that this is 44 cents. We're not going to look at this as necessarily our coordinate plane, but as a graph. So all those from 0 up to 1 ounce, and including 1 ounce, you're going to pay 44 cents. Now, if it's anything over 1 ounce, then you're going to have to pay 67 cents. And if it's 1½ ounces, you pay 67. If it's 1 3/4 ounces, you pay 67. If it's 1 7/8 ounces, you're going to pay 67. All the way up to 2, then you're going to pay 67 cents. Now we're going to put an open circle here at 1 because 1 ounce you pay 44 cents. But then all those others up to 2, you're going to pay 67 cents. If your letter weighs over 2 ounces but up to 3 ounces, anything above 2 all the way up to 3, you're going to pay 90 cents. And again, it doesn't matter about those in between. If it's 2½, you still pay 90 all the way up to 3. And at anything over 3, then it's going to jump up to $1.13. And so we have, whoops, down here. And so this is an example then of what we would call a step graph. Is we don't deal with what happens in between there. We didn't pay anything that cost. Weren't going to pay 54 cents because it was 1½ ounces. It didn't matter. Anything between the 1 and the 2, you're going to pay the same amount. Y'all do this on your cell phones. If you talk for for 30 seconds, you still pay for 1 minute. If you talk for 1½ minutes, 1 minute and 30 seconds, you're still going to pay for 2 minutes. As soon as you've talked 1 second over your minute, then you're going to be charged for the next full minute. They don't charge you for 15 3/4 of a minute. They would charge you then for the 16 minutes. And so that would be, again, an example then of a step graph. When you go to pay your income tax and you look at your chart, they will tell you, if you have made up to this certain amount, then this is what your tax is. And then they'll give you another one and it goes to a different level. So there's a lot of areas where you deal with graphs that would be what we would call a step function. Now, one of the most common ones that we deal with is a greatest integer function. And when you see for the greatest integer, you're going to have some special symbols. One of the symbols will look like a brace, but it's going to have a separate line in there. It's going to be a brace, and there's going to be an extra line in there. And so you'll see that symbol. Sometimes you'll just see a brace around the x, and that's going to be greatest integer. Another way that you'll see it is y is equal to, and it'll say integer x. On a lot of your calculators, then that's the function you look for, is integer x. Now what we mean here is we're looking for the closest integer without exceeding the actual value. And one way that you can do this, it's real nice if you do it with a number line as you're thinking about it. We usually don't have any trouble when we're talking about positive numbers. It's when we start getting into the negative numbers that we have a little bit of a difficulty. So we're going to go through a few and we're going to see what we mean by the greatest integer. We want the closest integer without exceeding the actual value. So let's say that we want integer 5 3/10. Well, if we look on our number line, 5 3/10 is here. We're wanting the closest integer without exceeding it. Well, that would be 5. But let's say we want integer 5.95. Well, right here, that would be about here on our number line. We want the closest integer. Well, if we were just wanting the closest, it looks like 6 is closest, but 6 exceeds 5.95. So we have to go down to 5. It's not rounding. Finding the greatest integer function is not rounding. It would be more what you would call truncating when it's positive. We go back to the closest integer. Our answer can never be bigger than what we began with. If we wanted integer 5.01, well, again, that would still be 5. We want the closest integer without going over. Now, let's look at some negative ones. And I'm going to use the other symbol just so that you're are familiar with it. Let's say that we wanted negative 2.1, or 2 1/10. We want that greatest integer. Well, here would be negative 2 1/10. So we want the closest integer without exceeding. Well, now if you went to 2, you've just exceeded it. Remember, as your numbers go to the right, they get bigger. So our closest integer would be negative 3. And if we did negative 2.7, oops. Again, negative 2.7 would be down here, but if we went to negative 2, we've exceeded it. We've gotten bigger. So we would go to negative 3. What if we wanted integer 25 hundredths? Well, that's right here, or 1/4. It's right here. So the closest integer without going over would be 0. So you need to be able, given a greatest integer function, to evaluate it. And we're not going to be dealing so much with graphing them at this point, but you do need to be able to evaluate them. And if you did graph them, then they would be another example of a step function.